Et nous avons le plaisir d'accueillir comme première conférencière Claire Gardent, qui est directrice de recherche CNRS au Loria à Nancy, et qui va nous parler de verbalisation multilingue de graphes de connaissances vers des langues bien et peu dotées. Claire est très connue dans la communauté française et plus largement internationale de traitement automatique des langues et a reçu la médaille d'argent du CNRS il y a 2 ou 3 ans, je ne sais plus exactement. Claire, tu me corrigeras. Claire, tu m'entends ? Claire, ton micro est coupé et je ne sais pas si la connexion est bonne.
Voilà, vous m'entendez?
Ouais, c'est très bien comme ça. Moi, écoute, je te donne la parole et puis on se revoit dans quelques minutes, quelques dizaines de minutes pour des questions et des échanges.
Ok. Alors, j'avais prévu de faire la présentation en anglais, parce qu'on m'avait dit en anglais.
C'est parfait, c'est parfait, c'est parfait si tu la fais en anglais.
Okay, so good afternoon, everyone. Thank you for the invitation. Thank you for the kind introduction. I would have loved to come to Grenoble, but it was impossible. I was teaching in Nancy, and so there was no way I could transport myself to Grenoble in time. So today I'm excited to talk about our work on verbalizing graphs into high, medium, and low resource languages. It is part of some work we did within the framework of the XNLG AI chair, which was focusing on generating from multiple sources into multiple languages. And the work I will present today is in collaboration with the list of people that is shown here on the slide. And the work was co-funded by the ANR, the Région Grand Est, and Meta Facebook. So structured data that we use in NLP exists in many forms. So for example, we have knowledge graphs such as Freebase and Wikidata. We have RDF stores. We have graphs as meaning representation designed by linguists. Tabular data can also be seen as graph data. And there are lots of advantages to this structured data, like it's a really intuitive way to represent relationship between entities. And it has a wide range of applications, such as, for example, question answering. And so the main question I want to talk about today is how we can take the structures and generate multilingual text from it. So in comparison to previous work that focus a lot on English, we are going to take it multilingual. And I will talk about 2 types of graphs, so not just knowledge graph, but also linguistic graphs, so abstract meaning in particular. So I will focus on abstract meaning representation, AMR, which you have an example here, and knowledge graphs, which represent knowledge about the words using a set of triplets or facts. And you have an example here, a sort of Wikidata graphs that describe some information about an astronaut called Alan Bean. And so in both cases, what I'm interested in is, again, how we can generate multilingual text from these graphs. So before I start talking about the contribution we made on this different, before I get to our contribution, I first want to discuss the challenges that we are facing when we address this task. So the first challenge is that the structured input has a very different surface form. So if you think about machine translation, when you have machine translation, the input is a text and the output is a text. Here we have to map a graph into a text. So that's the first challenge. Second is that the structured input is often underspecified. So if you go from an RDF graph to language, there's a lot that has to be reconstructed. And similarly for AMR graphs, which are underspecified with respect, for example, to tense or to numerical quantity. And so when you generate from this graph, you have to somehow reconstruct the missing information. A third challenge is that, again, different from machine translation, we don't have naturally occurring parallel graph text data. So again, for machine translation, you can find on the web, you can find translations that give you this parallel data that you need for training your model to go from one language to another. But for graph text data, it simply does not exist. You have to create it somehow. And the fourth challenge is, because we are doing multilingual decoding here, that we have to decode into languages which have vastly different morphology and word order. So those are the challenges we've been working with these different years. And so how do we do this? So in this talk, I'm going to go over the modeling improvement that we propose to enable those tasks. And I want to do this in several steps. So I will start with a simple example that shows how we can use multilingual techniques for multilingual neural approaches or neural generation to decode from AMR graph into 21 languages. And from there, I will go over various evolution of the field, which show how we can address the problems that are raised by mid-resource or lower resource data languages. So I will start in a second step. I will show how pre-training. So in the first step, we don't talk about pre-training. Second step, I will show how pre-training and fine-tuning really change results or improve results really drastically on RDF to text generation going into English and Russian. And in the last part, I will focus on the generation into low resource and medium resource languages for both AMR and RDF graphs. And I will focus and I will show how you can use parameter efficient fine-tuning method to handle those languages which have less resources. I will start by talking, first I will talk about generation from RDF graphs going into very low resource languages, including Breton. And I will conclude with some work we recently did on generating from AMR graphs into 6 high and 6 low resource languages, where the idea was really to be able to compare what was happening, you know, when you compare those high versus low resource languages. Okay, so first the work on AMR so multilingual AMR verbalization, which is already quite old. It's some work I did with Angela Fan. So here we start from an abstract meaning representation, which is a linguistic representation that was designed by linguists to represent the meaning of a sentence. And here you have an example for the sentence. Ryan described himself as a genius. And the graph, the MR graph is on the right side. And you can see this graph, the node of this graph are concepts, are labeled with concepts. And the relationship between the nodes are semantic relationship. And what we want to do is we want to verbalize this graph, as I say, into 21 languages because of the data set mainly we are using, which is a Europal data set. So we worked on this task, how to verbalize the MR into 21 different languages. And the languages covers, what we were also interested in is those languages cover different families, so Romance, Germanic, Slavic, and Uralic. And we were expecting to see differences in results between those languages because they have very different word order and morphology from English. So when you work on, so the kind of task I'm looking at is what's called conditional text generation, meaning that you generate text from some input and you have to respect some constraints that are given by the input. And you can use a decoder for this, but the more traditional approach is to use an encoder-decoder. So the idea is that instead of using a single network, you have two networks. And the first network, the encoder, is trained to build good representation of your input, to build a numerical representation of your continuous representation of your input. And the decoder is going to take this representation of the input to generate the output text as a function of the input. So we assume this encoder, so we use an encoder-decoder framework, so consisting of an encoder and a decoder. So how do we encode AMR? And so here the goal of the encoder is really to build representations that are good for the task, that allows us to provide a representation of the AMR graphs that will favor good output quality text that is faithful to the input. So how do we encode those AMR graphs? We use a transformer encoder, and then we do several things. So the first thing we do is we linearize the graph. So we transform the graph into a string, a sequence. We add structural embeddings to capture the structure of the graph to the model, to the transformer. And we do some pre-training. So using the mass language modeling objective on 30 million silver AMR graphs. So I'll go into more detail about each of these steps. So the first step is to linearize. So you start with, you have your graph, and basically you do a traversal through that graph, you collect all the tokens, and you end up with a sequence of tokens. So this is the graph, the linearized graphs that we are working with. However, if you do this, you lose important information about the graph structure. So in particular, you don't know, you lose any understanding of which nodes are related to which nodes. So to supplement this, or to address this limitation, we added to the transformer encoder some embeddings that are that were designed to capture, to compensate for this lack of structure in the input stream. So to capture the structure of the graph. So in the same way that if you use a transformer encoder for text, you are going to add to the token embeddings, you are going to add positional embeddings. In our case, we don't use those positional embeddings because position in the graph, I mean, linear position does not mean much in the graph. So instead, we use this structure, we add the structural embeddings to the tokens of the linearized graph. And we use two kinds of structural embeddings. The first embedding captures the notion of a branch in the graph. So you see on the left side of the graph, so the orange nodes in this graph, we all share the same branch embedding. And the second type of embedding we add to the tokens is a sibling embedding to capture the sibling relationship between nodes. So here, all those nodes here will have the same sibling embedding in the input sequence. So this is for the encoding. Now, how do we decode? What we want now is to have a decoder that is good at decoding into multiple languages. So on the decoder side, what we did is we use cross-lingual embeddings, which come from the XLM paper. And the idea of this paper is simply that they use a mass language modeling objective, such as similar to BERT. But they also use a translation objective to train the X-lingual embedding, to train the cross-lingual embeddings. And this is useful for us because we are going to do multilingual decoding. So we're going to decode into words of different languages. So we want to have those cross-lingual embeddings that brings synonym words across languages into the same position in the vector space. And finally, so this is the encoder and the decoder. And then finally, we leverage pre-training, because at the time, pre-trained model did not exist. We didn't have models like T5 or MT5 or BART for encoding, decoding. So we leverage pre-training both on the encoder side and on the decoder side. So on the encoder side, as I say, we're going to train the graph similar to the way BERT is training word embeddings. That is, we use this mass language modeling objective on graphs. We basically create a large set of silver AMR by taking a corpus in English and using a semantic parser that can automatically produce AMR graph from text. So we do this pre-training on silver AMR for the encoder for producing these AMR graph encodings. And for decoding, we do, on the decoder side, we use causal language model pre-training, but we do this on all target languages at the same time so that we have a pre-trained multilingual decoder. So it's similar to what's happening to the more recent approaches to multilingual translation. You just put all your training data in one pot and you train your model on this. So the model is trained to decode into multiple languages, and then each training instance is prefixed with a control token, which indicates to the decoder what language it should decode into. So this is a model for multilingual generation from AMR graphs. how do we train? So we need some training data, and as I said, there is no naturally occurring training data for AMR to text generation. Well, there is some, so there's no naturally occurring one. There is some data for AMR to English, but there's no data for AMR multilingual to multilingual. So what we did here was use the Europal corpus, which is the corpus of the European Parliament, and it contains 21 languages of the European Parliament proceedings, and then we applied our semantic analyzer to the English part of the corpus to create the corresponding AMR graph. So we have one AMR graph that we derive from the English text or sentence. And then since this English sentence is aligned with sentences in 21 other languages, we now have a parallel corpus that maps an AMR graph to its verbalization into the 21 European languages. And in this data set, I would distinguish between, so there is about half of the languages in this data set I would consider high resource languages, such as, for example, French, English, and German. But there is another half that is more like mid-resource because many countries joined the European Union later, and so there's a bit less data for these languages. Okay, so this is the data that we are going to train our models on. And for the evaluation, we stick with two sources. So we reserve a part of this CIVER data that we created from Europal for testing. And we also have a corpus, an available corpus where the AMR have been written by linguists. So they are what we call gold AMR. And each AMR is associated with 4 languages, of which 3 are in our data set. I think it's English, German, and French. Okay, so then we trained our model on this training data, and then we compared our model with 2 different baselines. The first baseline is comparing what happens if you train separate models for each language versus our multilingual models that trains on all languages together, which could introduce some noise. So here we would compare our multilingual model with for example, the FR, the French token for decoding, with what we call a bilingual baseline, where you want to translate an AMR into French. So in the first case, you train only on the French data. In the second case, you train on all the data for all 21 languages, but at decoding time, you ask the model to decode into French. Right. So here are the results that when we compare, so now here, this is a result on the Europal data set, on test set, and the gray bar is for the bilingual model and the blue bar for the multilingual model, so for our model. And you see for English, our multilingual model is doing a little bit less, a little worse than the bilingual or monolingual model. But in general, the multilingual model generally outperforms the monolingual model. And you also see that the difference is bigger for what I call the mid-resource languages. So those for which we have fewer training data benefit from transfer more. So they benefit from transfer in the multilingual model. So we also evaluated on the gold AMR data set. And here you have similar results. So for English, the results are a little less good for the multilingual model because presumably some noise was introduced by the multilingual data compared to the monolingual model, which is usually stronger anyway. But then for the other languages, usually the multilingual model is a bit better. Another natural baseline we had to compare with was what's called the generate and translate baseline. So the idea is we saw that generating from AMR into English generally gives good results. So a natural baseline is to say we're going to first generate from the AMR into English using those models, and then use machine translation to translate the English output into the target language. Right? So you first generate into English, then you translate the English into the target language. And in comparison, so it's a kind of pipeline model, which also requires that you have a translation model for your target language, compared to a multilingual model, which is an end-to-end model. And here again, as a result, so those are the results on, yeah, so here there are fewer languages because at the time, we basically focus on the machine translation models that were available and of good quality. And so these were the languages we had those machine translation models for. And so here again, you see, our models are sort of on par, a little bit better, sometimes a little bit worse, but they are not, they are, on par, say, with these hybrid translation models, which is actually quite good because the translation models, here we are training on a few 100,000 instances for each language, whereas the machine translation models that we used at the time, they had been optimized for years and they had been trained on millions of instances. So it's actually a baseline that is very, this hybrid translation, hybrid generate and translation baseline is actually a very hard baseline to beat. We also did a human evaluation, which was actually very difficult because we had all those languages. So it's not something you can do using crowdsourcing. And also we wanted to really have the evaluators check whether the word order and the morphology was correct. And so we needed some people with more or less linguistic expertise because we had, you will see the question requires some linguistic knowledge. So we decided to recruit our colleagues and we sent out emails on the NLP mailing list and linguistic mailing list, asking people to help us out with this human evaluation. But because we did this, we could not have a very large scale evaluation. So we asked people to evaluate 50 sentences per languages, asking people who were native in these languages to provide us with some information. So we had, for each languages, we had 50 sentences that were evaluated by a varying number of evaluators, depending on the language. It could vary between, say, 5 and 15 evaluators. And so we asked them, because the scores only say so much, so we really wanted to have an idea of the quality of this generated output, other than just a score. So the first question we asked them is semantic accuracy. So we know, language models are very good at producing, good quality text, but we also, in this case, in conditional generation, there is a strong constraint that the generated text must actually match the input of the input graph. Right? So it should not contain more information, it should not contain less information. So the first question we asked the annotators to give us a ranking for, a score for, was semantic accuracy or faithfulness. Does the generated text correctly paraphrase the reference? So we did not give them the graph, we gave them the reference because we had it, so the text in the Europower proceedings. The second question was about morphology. We wanted to check, is the morphology correct? So are the argument constraint respected? So for example, does the verb agree with the subject in French or the noun with the adjective? And finally, we asked them, is the word order natural sounding? And here, I just give you the results for the semantic accuracy, but more or less they are this, similar for the other two questions. And you see 2 is like a minor error. So they had this scale from 0 to 3, right? So 2 was like minor error. And so you see overall the scores are pretty good for all languages. So some languages are a bit lower, but in general, the quality is actually quite good. Well, I didn't give you some examples here, but another thing we saw is that the model was very good at paraphrasing the input, presumably because the input is a little bit underspecified, and so it allows more for more variation in the output. So the key takeaways from this first work was that pre-training and multilingual techniques, so this cross-lingual embeddings, multilingual encoding, decoding, or multilingual decoding, really allows us to bridge the gap between those English-centric AMR graphs and the target languages, which very varied syntax and morphology. Another takeaway was that multilingual models benefit from increased training data and perform better on average than bilingual. It's also a result that is not well known from the machine translation community. And in our case, as a multilingual end-to-end model outperforming the hybrid generation and translate model. Okay, so that was the first part about how basic methods that we use in multilingual neural approaches allows you to verbalize graphs into multiple languages without using pre-trained model. So now I want to talk about how the pre-training and pre-trained models really change the picture. I mean, really allow for huge improvement in conditional generation. And I will start, so in the second part of the talk, I will focus on RDF to text generation. And I will start by introducing the web energy share task and show how pre-training and fine-tuning has this drastic impact on generation results for, in this case, for English and Russian. Okay. So the web energy challenge was initiated in 2017 and was motivated. So we had two key motivations for starting this challenge. The first one was to encourage the development of models that could verbalize the content of knowledge graph, or more specifically RDF stores. But the second was to test generation model on their ability to address what was known at the time as a micro-planning problem, which in a sense you can summarize as producing good quality text. So of course today with large language models, this is much less of a problem. We know how to generate high quality text, but still the task remains a challenging task with respect to factuality. So I mentioned for AMR, one key issue is semantic faithfulness. Similarly, for when you generate from a knowledge graph, you want the generated text to actually match the graph. And in fact, what we find still today, is that the best models still are not factual. They still make mistakes. They still produce text that is not faithful to the input graph. So in the first challenge, the first version of the challenge in 2017, we focused on English. And so the task was how to generate an English text from an RDF graph. And for this, we created a training and test set where the graphs were taken from DBpedia and the English text were crowdsourced. So we paid people to write the text that would verbalize each given DBpedia graph in the training and test data. And so when we created the test data, one important thing we took care of was to create challenge test sets that would allow us to test the ability of the participating model to generalize to unseen data. Unseen data meaning graphs which would contain entities not seen in the training data, and entities or entity categories not seen in the training data. So this was the first version of the challenge. So we had a small number of participants. 6 participants submitted 10 systems, and at the time we still had rule-based system. We had a statistical machine translation model, and 5 neural models. And here you see the results of each of the models. And in green you see the blue score. And here in green, you see the result on the whole benchmark, on the whole web energy benchmark. In blue, you see the result on the part of the benchmark which belongs to the seen category. So all the entities and categories had been seen in the training data. And in red, you see the result on the unseen test set. And we see 2 things, basically. We see that the different models have very different results. So you have some models that are very poor, some models that are much better. So there's quite a wide range of results across the models. But the other things we see clearly is that all models degrade on unseen data. So at the time, the task was actually quite difficult. And it remains difficult actually on unseen data. So in 2020, we had a second issue of Web Energy where we generalized the task in two different ways. First, we generalized to Russian, so we asked people to generate into English and Russian, and we also offered them the opportunity to provide results for the reverse task, so generating RDF graph from English or Russian text. So we extended the training data, we had more categories, so it got a bit bigger, and we created new unseen test set. So this time the task was known, the data set was known. It was 3 years after the first version of the challenge. And we have 17 teams submitted 48 system runs. And you can see all the big players participating like Google, Facebook, Amazon, and some of the key universities working on generation at the time. So here you have the result, and in this time it's the minimum and the maximum blue score on the for each of the languages and each of the benchmark. So the first thing we see is the results are better for English than Russian. So remember, at the time people were using pre-trained models, so this shows that the pre-trained models pre-training is still much better for English than for Russian. But we also saw, if you compare with the result we had in 2017, you see a huge increase of results, so plus 16 blue points for English when you compare this pre-trained model with models that were not pre-trained. So in 2023, we had the third version of the task, which focused this time on low resource languages. And so the low resource languages were Breton, Welsh, Irish, and Maltese, so with varying degree of low resource, Breton being the worst. And so this time we created the dev and the test data, but we didn't create any training data because it was just too costly and too difficult to find translators who would do the work. So we had about 5 participants, submitting for different combination of languages, some for all and some only for Russian, some only for Maltese. But really what the important difference here was there was really no training data. We provided several training data that we created using machine translation, but it was really poor quality, especially for Breton again. So what people did, they tried fine-tuning on the very small bit of dev data or on machine translated data, but still the result was so poor they just did not submit those fine-tuned models. Instead, what they did is again develop this pipeline generate and translate model, where basically to go from RDF to English, they train T5 or MT5, fine-tune on the English Web Energy data, or they use ChatGPT in context learning with no fine-tuning, but ChatGPT probably has seen all the Web Energy data. So this was for going to English. Then for English to low resource languages, people use NLLB machine translation, so the No Language Left Behind from Facebook, or Google Translate. And here are the results again. So it's the minimum and the maximum blue score for each language. In blue, you have the English. So you see, the results, you have strong degradation with respect to English, of course. But yeah, what you also see is a very poor results from Breton. So, you have this score of 1 blue points for Breton. So it's really garbage. So given this, we started thinking about parameter efficient fine-tuning methods for, trying to improve those results. So what I just said here, so one problem with Breton is the machine translation model was very, very bad. So if you use this energy plus MT pipeline, you get very bad results. If you try full fine-tuning, you still get very bad results. So what we did was this parameter efficient fine-tuning method, where we combine a prefix tuning approach with, we modify the prefix tuning approach with by structuring the soft prompt with to model some knowledge about language families. Okay, so the idea of prefix tuning is instead of fine-tuning the whole pre-trained models that you are using, you're going to fine-tune a small set of parameters, which we call the prefix. So how do we integrate phylogenetic information, so information about language families into a soft prompt? We just, structure the soft prompt. So the soft prompt is just a sequence of parameters. We just structure the soft prompt to capture information about family, genus, and language. So here you can see, those two languages are sharing a genus, are sharing a family. And the idea of this structured soft prompt is that during training and fine-tuning, the corresponding parts, so two languages that share the same genus and family, will contribute to updating that part of the prompt, the relevant part of the prompt. And so the idea here was to allow the low-resource languages to benefit from the training data of the related languages, because the corresponding soft prompt will be updated by these two languages. So the hope was to facilitate transfer with this structured soft prompt, but at the same time to prevent the mixture of training data to introduce too much noise in the model. And so we train and test. We train in two steps. First, we train language models. So we do self-supervised training of the language model on monolingual data to pre-train the soft prompt. And the second step, we further fine-tune on the downstream tasks, so the RDF to text data, for which we don't have so much data, but we do have some. We use the dev data. And of course, at inference, we initialize the soft prompt with a corresponding with the correct subprompts. And here you see the results. So again, it's a blue score, and we're comparing three approaches: a state-of-the-art control prefix approach, the vanilla full fine-tuning, and our approach. And you see the differences for Breton, Welsh, and Irish. So we're doing a little bit better. Not so much better, but a little bit.
Claire, you still have 5 minutes, if it's okay with you?
Okay, yeah, I'll try to finish in time. 5 minutes, okay. Yeah, I'm almost there. So the key takeaways here: pre-training improved performance. So that's the gap between 17 and 20. Performance degrades on out-of-domain data. So we saw the performance degradation on unseen data, and the performance is still very poor on low-resource languages. And parameter-efficient fine-tuning helped a little bit. So in the 5 minutes I have left, I will go quickly through the last one I wanted to present. So it's again a parameter-efficient fine-tuning approach, where we consider generating from AMR graph into high and low resource languages. And here again, the idea was to use knowledge about language families to improve learning. So what we do here, we don't use prefix tuning, we use a low rank adaptation. And basically what we do is we're going to do some iterative low rank adaptation. So maybe I should go to the model. Yeah. So low rank adaptation is this thing here. So you have your pre-trained model, and you have your low rank matrices that you are going to update during training. The pre-trained weights are frozen, so you don't touch them. You just update those weights here. But what we do is at the end of a fine-tuning step, of a pre-training step, we can merge these matrices here with a pre-trained weight to create a new model. And so we use this, the fact that this Loria adaptation allows us to derive a new model for an existing pre-training model to do iterative training, taking into account how closely related or using different sets of training languages. So if I go back here, what happened, the key idea was we first train a multilingual model on all 12 languages. So we have 6 high resource languages, 6 low resource languages. And what we want is to end up with models that are good both for high and low resource languages. So what we do is we start by training on the 12 languages. Then we do Loria adaptation of this model. So we derive 2 models. One training on 6 Germanic languages and another training on 6 Romance languages. Using the Loria technique, we create a new model for these 6 languages, which we then further fine-tune on pairs of languages in this case. And the pair of languages are putting together a high resource language and a low resource language. So we want to maximize the transfer between those 2 languages. And here you see, so you have the comparison with the baseline being either a monolingual model, a multilingual model, a generative and translation models that we saw before, or a different version of the approach we propose. Basically, in general, what we show is that so our approach is those 2, the last 2 on the right. What the results show is that the approach outperforms or is on par with multi and monolingual approaches, but it outperforms the generate and translate approach from low resource languages. We also, so this graph here, which I won't have time to discuss in detail, just shows that this hierarchical Q-LoRa adaptation optimizes much faster than the free baselines, and on average, it outperforms those baselines. Then we also compare with previous work, but for previous work, there was not so much data, only for 4 languages. So if we compare with those 4 languages, which are high resource languages, we see that we compare on par with, we perform on par with them. So to conclude, I think if we want to go further with multilingual verbalization of graphs in general, what we really need is a cross-modal multilingual graph text similarity matrix that will allow us to filter noisy training data, because we do have some noisy training data available on the web. It allows us to guide generation using, for example, reinforcement learning. And it is necessary if we want to generalize graph-to-text model to other languages and to larger domains. And I'll finish here.
Thank you very much. So thank you very much for this very nice presentation, quite insightful. We have time for just a few questions, so please do not hesitate to ask questions if you have some. So I'll start then. Is hierarchical Q-LoRa the best way to do transfer from, in the case of low resource languages? Is it the state-of-the-art method currently?
No. I mean, this is the best we could do. There's not, we can't compare with very much because there's not much work on AMR multi. So this was generating from AMR, right? So we don't have the point of comparison. So the only point of comparison was what I show at the end. You know, this. Where are they? These 4. You know, when you train on this. But here they had training data. So these are high resource languages, right? And this is the only multilingual we have. Or the other multilingual is what we did with Angela in 2020, which again is has much lower results. But so we can't compare with anything really. But we did try to. So since we had this prefix tuning approach for the RDF to Breton thing, we tried to use it there, and it didn't work. Okay. And I'm not very sure why, but it really wasn't working. Okay. We tried and tried for months.
Interesting. I don't know what they are using in machine translation, because they are also interested in this issue with low resource languages, translating into.
Yeah. I guess, I mean, I'm trying to think what, no, I don't have any good, I didn't see any similar work using, I mean, people use adapters a lot in machine translation, I guess.
Right.
But this idea of having this, stacked LoRa, hierarchical LoRa approach combined with the choice of training languages guided by language families, I haven't seen before.
I haven't seen it before, so yeah. Oh, that's interesting in any way to try and use the phylogenetic information for languages. That's for sure. Yeah. One last question. Yes.
Thank you, Claire, for this nice presentation. I have one question about the metric you use to measure the performance called BLUE. In our team, we use GPT as a judge. Do you think it's an option to use for, let's say, a better precision in the results? Because sometimes if we just take it corresponding words, maybe the meaning, I mean, if we compare meaning, I don't know how to say that.
Yeah, I know what you mean. BLUE is not a very good metric, right? Because it's just looking at the string.
Yeah.
And so, in fact, in the AMR work, when we looked at the output was very different from the reference. but it was good. It was a paraphrase, you know, it was a really nice paraphrase. So probably it had bad blue score. So there's ChatGPT. Yeah, I'm not sure. I mean, on low resource languages, I have a very strong doubt about what ChatGPT could tell us,
Okay.
right? I mean, because there are work on, you know, using ChatGPT for evaluating RDF to English, so that, you know, that, or knowledge graph to English, because then you can ask, does the text mention all the entities present in the graph? And so there is the C-score, I think C-score metrics that does this. But if you want to do this on low resource languages, I don't think it's going to work.
Okay, thank you.
Okay, okay. So thank you very much. We hope to welcome you in Grenoble soon, because I'm not sure you have come to Grenoble recently. So thank you very much again, and hopefully we welcome you in person.
Okay, thank you. I would have loved to come, but really not possible.
Yes. Okay, so we move to our next speaker with Martin Lenglet, who is going to talk about exploring latent representations to push the boundaries of supervised neural text-to-speech models. And for this session, we are alternating in between, let's say, more experienced speakers and younger speakers. And Martin is one of our younger speakers.
Yes, indeed. So by the way, thank you for having me today. Yes, I'm a young researcher. I have finished my PhD a few months ago. But I'm sure you will like our work that I've done in collaboration with Gérard Bailly and Olivier Perrotin in the GIPS lab. So I will be talking about the methods we have proposed to explore the latent representation of neural TTS. But first, I would like to start by positioning this work into the wider field of generative AI. Because to be honest, I was a bit surprised to be invited in this generative AI session, as I've never really considered that the text-to-speech models I've been working with were part of this wider field. Because indeed, to my understanding, generative AI are models that are supposed to be able to generate content of various forms, or I should say human-like content. It can be audio, visual, text. But more specifically, this content is supposed to be generated through the natural interaction with the user. And so this is done by training on an extensive corpus and using, in general, large language model to interpret this natural interaction. On the other hand, this vision is opposed to the one of supervised model, which are more specific model like classification or prediction, for example. Here's an example of image classification. And supervised models are designed and evaluated on very specific tasks, which require specific and carefully annotated corpus and specific architecture. And the neural text-to-speech model lies in this category, because in this most basic form, the text-to-speech framework can be illustrated as this two-step process by first converting input text through an acoustic model into speech representation or audio representation. Generally, we use mail spectrogram as audio representation. And then using another network, a vocoder, to convert this mail spectrogram into an audible waveform. So for the sake of simplicity in today's presentation, I won't cover the role of the vocoder because it is widely admitted that the well rendition of the mail spectrogram is enough to ensure the natural character of the generated data. Though there have been a lot of success through this approach with models like Tacotron 2, FastSpeech, and FastSpeech 2 that are still widely used both in research and in real-life applications. To be a bit more specific, this acoustic model may be seen as also as an encoder-decoder architecture, with the encoder being used to contextualize the input sequence through the use of various neural layers. It can be a convolutional recurrent layer or more recently transformer layers. So this encoder introduces local and global context into the input sequence to generate. And this contextualized sequence is consumed by a decoder, which basically can use the same neural layer as the encoder to generate the sequence. And one of the key aspects of the TTS models is the text-to-frame alignment, because generating audio from text is a sequence-to-sequence approach with sequences of different lengths. So you need to learn either implicitly through attention mechanism or explicitly through duration predictors how to align the input characters into the output spectrogram frames. So this approach fully set this kind of model into the generative AI field, into the supervised AI field, but can it also be compatible with generative AI? So my main concern with this aspect is that this kind of model is fully deterministic. So it cannot, it is really an obstacle to the generation of variability, which is needed in those generative AI. So one answer to this obstacle has been seen through the introduction of diffusion model into the TTS field. So diffusion, in a nutshell, are models that are trained to recover clean data from artificially noisy data, and they are guided, in the case of generative AI, they are guided by a prompt, which is text rated in like as a natural language, and which is used to guide the reconstruction process. Applied to the generation of speech, this same architecture can be used with an initial Gaussian noise, which is also biased by the output of an encoder, which is very similar to the one I've been discussing before. And so this model, I would say, fit more into the generative AI field, even though the natural interaction may be contested, because of course you have to input text written in a natural way into the input, but it is more a necessity due to the speech you want to generate than the conveniency implemented for the user. Similarly, I would say that the models that are used to learn expressivity through to learn expressivity for TTS also fell into this category. For example, Scary Ryan have proposed what is an additional layer, which is called a reference encoder, which is supposed to learn a compact acoustic representation from the audio sequence. And from their own vision, they see this model as a sort of autoencoder-like model which learn a compact representation of the audio signal, which is biased by the text to generate new example of speech at the inference stage. And so I would say that this kind of model do lie in the generative AI field. So now that I feel a bit more comfortable about talking about text-to-speech model as generative AI, let's talk a bit more about what have been the focus of my PhD in the last 3 years. So I've been working on expressive synthesis, so a few words of what is expressive synthesis to begin with. So expressive synthesis generally refers to the speech adaptation to the context of communication. So it's a key element of the acceptance of synthetic voices in everyday applications. It can take various forms, the local variation of prosodic features like fundamental frequency, energy, duration, the emphasis on certain part of the sentence or on certain words, and the prediction of phonological variants. All these aspects may be controlled at the low level, so by explicitly choosing what feature to modify at what part of the sentence, or at the high level by choosing the appropriate attitude to express. And this attitude should have an implicit impact on the local prosodic feature you want to generate. Here is an example of what I call attitudes. So here is the same sentence spoken through a committed attitude.
Oui, les socialistes sont soucieux de l'épanouissement des familles.
Or through a thoughtful attitude.
Oui, les socialistes sont soucieux de l'épanouissement des familles.
So here you can see the differences. And what did I do to grasp more control over this expressive aspect? In fact, my approach was to analyze the latent spaces computed by neural TTS models and to try to find in those latent spaces what were the features that were encoded, how were they encoded, and this understanding and this interpretability of the latent feature gave us control over the feature found, as I'm going to show you in this first contribution. Then if we have time, I will speak briefly about how we adapted this model to the generation of audiovisual features to generate a virtual agent. And finally, also, if we have time, I would like to talk about the ongoing project Emotags, which is an innovative manner to constrain this compact acoustic space through semantics computed from a pre-trained language model, which ultimately leads to the free control, the control through free attitude tags of the synthesis. So here we go. Okay, so the interpretability of neural network is a very dense field in today's knowledge, in today's research. It has been partially discussed yesterday for ethic concerns, and it will be further described in a later presentation. But this interpretability is both useful in terms of research and in terms of control. For our work, we took inspiration from what has been done with acoustic representation from self-supervised models like Wave2Vec and Hubert. And for example, this study from Vaidya and colleagues so studied the evolution of this representation and the encoding of linguistic units into this representation, and found that the later layers do encode high-level phonetic units, high-level linguistic units like phoneme and words, and this explained why these representations are so performant in terms of speech recognition, for example. Similarly, Shaw and colleagues use linear regression to predict articulatory trajectories in those same models, and so we found that linear probing, so which refer to the combination of linear classification and linear regression, was an interesting way to explore these latent spaces, because it's relatively easy to implement, and it gives a potential for control through linear bases, as I'm going to show you. So how do we apply that to neural text-to-speech? So once your model is fully trained, the idea is that every new sentence that you generate do produce intermediate representation, also called embeddings. And so you can save all these embeddings. In the same time, we computed acoustic analysis of the synthetic speech by character to extract features of interest. And we then used multilinear regression to predict this feature from the intermediate latent spaces. Note that there are two cases here. Multilinear regression is used for continuous features, whereas LDA, or linear discriminant analysis, is used for phonological features, which are categorical. So you can see that this method is neither feature nor model dependent, which is very interesting to be applied in a lot of different cases. We have, as an example here, I will be talking about FastSpeech2, which is a transformer-based TTS model. And we have trained this model on a new segmentation we have proposed of the French MIAI Labs dataset. We used about 30 hours of speech from a single speaker. This corpus is also available online. And what is interesting with this corpus is that we have proposed also a one-to-one letter-to-sound mapping for every sentence of this corpus, which is an alignment between the input sequence of character, which is the orthographic input, and the expected sequence of phones that should be produced from this input with the one-to-one mapping. And we were able to use this alignment to train the linear predictors from the linear discriminant analysis. So more specifically, the idea is to train the for each embedding, we train a linear discriminant analysis classifier and evaluate the performances of this classifier, and the performances indicate in which layer these features are encoded. I take the F1 score as an evaluation of the goodness of fit of the classifier. And here are the results presented from the left to the right, so the encoder on the left and the decoder on the right. And here you can see that the phonological features, so how phones, vowels, consonants, silences, and liaisons are encoded. They are encoded very quickly into the first layer of the model. So you can see specifically then that vowels take a bit more layers than stop consonants in yellow to be encoded. So it's not surprising because each vowel character can take a lot more variability than can generate a wider variability of phones than each stop consonant. And so you can see that even in absence of explicit task, at the output of the encoder, the embeddings that are computed by the TTS models are very good options to predict phonological features. So this interpretation of in what layer are encoded each kind of linguistic parameter is a first step into the design of new meaningful tasks using this representation. So for example, we could use this representation to compute explicit phonetic prediction. So this is what we have done for the model we have presented to the Blizzard Challenge 2003. The idea is to add an explicit task of phonetic prediction at the output of the encoder. So basically, this idea helped us training the model on orthographic and phonetic pairs without the need for audio references. So which is very interesting to train the text encoder on a lot of various contexts that are hard to find in audiobooks corpus, for example. We found a general accuracy of 98%, which matches the state-of-the-art aligner performances like eSpeak. But more specifically, this training on a particular context helped us disambiguate between homographs in the presented corpus. So homographs are words that are spelled the same but are pronounced differently. And for example, this result found showed that we were able to disambiguate between homographs that are very difficult even for models that are evaluated as very accurate, like for example, convie ou convient is a very difficult task for TTS, whereas our model was able to make the difference.
Mais plutôt arrêté à une époque qui convient à son timbre.
Qui convient, and the other case.
Les créatures ensorcelantes qui habitent convient le visiteur à pénétrer l'univers parallèle de l'artiste.
So just because of the context, the text encoder were able was able to determine the good variants to pronounce thanks to this additional task. Similarly for continuous feature, so I was talking about how we predicted this feature into the successive layer of the model. So we use a kind of similar approach, but instead of linear discriminant analysis, we use linear regression. And here, the goodness of fit is evaluated through the R-square, which is an evaluation of the residual error after the prediction. We could discuss about the patterns of encoding into the successive layer, but I won't have time to go into much detail in today's presentation. So I will instead focus on the controllability aspect, but we can go back to this slide later. On the controllability aspect, so the multilinear regression gives a set of coefficients that are used to predict a feature from the embedding. So on a geometrical perspective, this set of coefficients is the direction to move along to bias the model into thinking that it has to generate a different feature. Like, for example, if the fundamental frequency is encoded into this direction, if we move all embeddings into this direction, we are able to generate a higher fundamental frequency than before. So we can do this for every acoustic feature, but you have to know that this, the accuracy of this control is very layer dependent because the features are not linearly encoded in every layer of the model. And that's why we implemented this control at the output of the encoder. So all the results I'm going to present are implemented at the output of the encoder. So for example, for the control of fundamental frequency, here is an unbiased example, so the red one.
La devanture de presque toutes ces misérables boutiques était grillagée de fer.
With a higher F0.
La devanture de presque toutes ces misérables boutiques était grillagée de fer.
And with a lower F0.
La devanture de presque toutes ces misérables boutiques était grillagée de fer.
So you may note two interesting behavior with this control. First, yes, so I am. The plot here is the fundamental frequency by character, so it's a representation of the intonation along the sentence. And so the first behavior I want to talk about is the saturation effect. So in fact, we found that with this control, the model was not able to modify its features beyond the distribution of the features that has been seen in the training corpus. So it's a very interesting feature to ensure the naturalness of the speech and the speaker conservation. And also, you can see that the tone, the ending tone of the sentence has been modified. So with a lower F0, the initial rising tone is changed into a falling tone. And it is a behavior that has been learned by the model because in the training corpus, the falling tone co-occur very frequently with lower mean F0. So this unlinear effect is in fact profitable to the naturalness of the generated speech. We can do similar control for phonological behavior. So the LDA, which is computed, also gives us a main direction of the encoding of the switch between the two categories. And so by moving the embeddings along this direction, we are able to control the amount of switch. And so, for example, for the control of silences, you can see here that we are able to control between no and silences at every word boundaries. So here is the unbiased sequence.
Ce qui est sûr, c'est que maintenant que tu as mis le chourineur sous tes pieds.
Without any silences.
Ce qui est sûr, c'est que maintenant que tu as mis le chourineur sous tes pieds.
And with silences at every word boundaries.
Ce qui est sûr, c'est que maintenant que tu as mis le chourineur sous tes pieds.
So obviously, this control is not profitable to the naturalness of the speech, but it has to be used in a unified manner with the control of duration to be a more natural rendition of a lower or higher expressive style. And so, for example, we have here used this control in combination with the control of duration to mimic a slower speaking rate. And so you can see that in comparison with global stretching, which lengthen all the phoneme in the sequence by the same amount, this control introduce more natural pauses between words, even though the total duration is the same. So you can listen to the unbiased sample.
Son audace ne l'eût pas abandonné devant un tribunal ordinaire.
The stretching.
Son audace ne l'eût pas abandonné devant un tribunal ordinaire.
And the bias synthesis.
Son audace ne l'eût pas abandonné devant un tribunal ordinaire.
So hopefully you note that the introduction of pauses makes the overall synthesis more natural. So the general take-home message of this first contribution is that we have presented a methods to interpret what is linearly encoded into the successive layer of neural TTS. This method is very convenient because it can be applied to any continuous or categorical features and for any model. So we have tried other features, and we have tried this method on another model, Tacotron 2, and found similar results. This control is obtained through the post-hoc analysis, so no need for additional training, no additional data to have access to this control. But, as I said before, this control is less predictable, and so we were not able to find consistent differences between the perceptual evaluation of this system compared to an explicit approach. It is very dependent on the sentence which is evaluated. So more constraints could be applied using this method to, for example, avoid silences at one boundaries that are known grammatically to not being able to catch this silence. And we would also like to apply this method to other models, so that's why I'm happy to share this method with you today. Do we have time? Oh, okay, great. Okay, so we will now speak about the audiovisual generation. So how did we convert this model into an audiovisual generative model from text? So what have been done in most of the literature until now is a two-step approach, which is first using a TTS model like the one I've been presented to generate audio from text, and then use this audio, potentially augmented with the text, into a gesture model to generate movements from these combined features. The problem with this approach is that it implies suboptimal computation because you have to generate the whole audio sequence before starting the gesture model, and you also have the risk of asynchronicity between the audio which is generated and the visual features. It also negates the concept of coplane communication and intent, which can profit to models that implement unified representation. So instead, we propose this unified model, which is based on the fast-pitch2 architecture I've been presented. We have called this model FastLips. And this model introduced an additional decoder, which is a visual decoder, and reproduce the variance adapter, which is implemented in FastPitch2, but to introduce new specific tasks to focus the model on the rendition of lips. So to train this model, we need audiovisual data. So my colleague at the GIPSA lab have recorded this audiovisual data set of a French female speaker, which correspond to about 5 hours of speech recorded with this setup. And here are the results. So we have compared this approach to a more traditional baseline Tacotron 2 audiovisual model and find a consistent improvement over the whole synthesis. And we have also tried to explore whether or not the introduction of specific lips rendition tasks were helpful to the model, and also found some significant improvement when using these tasks. So here is an example of this lips generation quality.
Où sommes-nous dans l'Union européenne?
So I hope that people on Zoom have a good quality audio rendition. If not, you can have access to more examples through the QR code. Here's another example.
Et une petite abdication judiciaire qui ne dit pas son nom.
And for a more global perspective, here are two examples with the head of the avatar.
Ce sont les petits pas qui font les longues démarches. On n'éduque pas les enfants au rabais.
Okay. And so finally, we have some time for emotag. So, so as I said, the control method we have proposed in the first contribution through the introduction of post-hoc feature predictors for the different features and phonological features is interesting because it is versatile, but it is pretty difficult to target a specific attitude through this explicit control because it requires a precise tuning of this feature to match the desired attitude. And that's why the approach of Skyrian with its reference encoder was so interesting, because learning a compact acoustic representation through non-annotated data is very interesting. But the problem with this approach is that this compact acoustic space is very hard to interpret in terms of acoustic features and in terms of attitude rendered. And so we have proposed to create a model which introduces additional constraints to this reference space. And specifically, these constraints are based on a pre-trained language model to ultimately to allow the control of this feature through natural language. And to achieve this goal, emotags have three aspects, which is first the recording of an extensive expressively annotated corpus to be able to train this unified representation, and then to see if this collection of data is able to, if you can use this collection of data to design a unified model. So I will show you a few examples in a minute. First, the collection. Again, my colleague from the GIPSA have designed an online platform to collect these tags. By the way, this platform is still open and we still need some contribution. So if you want to participate into this collection, you are welcome. But up until now, this platform has enabled the collection of more than 9,000 free tags from more than 700 participants, which is a huge database for, especially for French expressive synthesis. And using stylus, mean square error loss to minimize the distances between the output of the reference encoder and the output of this adaptation layer, which takes these free tags into inputs. So we minimize this distance, and we are able to control the model with style tag or with reference speech. Additionally, we constrain this model even more through the use of a global style token interface, which is a way to project these embeddings into a set basis of 12 attitudes. So more specifically, for any input style that you use, this input tag will be projected into this basis. And this is interesting for two aspects. First, it ensures that any new token, even if it has never been seen before during the training, it can be projected into a well-known space, well-known area of the space for the model. And then it is also an interesting tool to explore acoustic and semantic proximity between unknown words. So, for example, if we use one of the attitudes that is part of the basis, the attitude is supposed to be correctly projected. So, if we use as input réconfortant, it is supposed to be just réconfortant. So, here is an example. Here is an audio example of what we are able to generate.
Je vous souhaite la bienvenue à cette présentation du projet MIAI.
And now, if we take an adjective that is not part of this basis, like dubitative, which is somewhere close to one of the attitude, which is incrédule, it is well projected more on this attitude than on the other, but it also introduces nuances that are meaningful both in terms of acoustic generation and in terms of semantics. So here is dubitative.
Je vous souhaite la bienvenue à cette présentation du projet MIAI.
And final example for amuser, which is also naturally similar to espiègle.
Je vous souhaite la bienvenue à cette présentation du projet MIAI.
Okay, so this was what I wanted to talk about in today's presentation. So I would like to thank Gérard Bailly and Olivier Perrotin for their meaningful contribution to this work. All the work, database and models that I have presented today are available online or will be available soon. And again, if you want to participate to the MIAI project, you are free to participate. Thank you.
Thank you. We have time for 1-2 quick questions. Yes, François. Can you pass the mic to François?
Well, I got it. Thank you very much. I was just wondering, maybe I missed something about the second contribution. I think it was between the lips and the speech. So I didn't really get if you learn that together. Is it a joint learning?
Yes. So the audiovisual model is trained from scratch.
Yep.
Up.
Yeah, Sinasky, indeed. Yeah.
So trained from scratch on audiovisual data, but it could be also trained on partially missing modalities.
Mm-hmm.
So we could have trained the audio model first and then fine-tune the visual model on visual data, because you are aware that visual data are more difficult to collect than audio data.
Mm-hmm.
But in this case, yes, the old version and also the baseline were trained from scratch on audiovisual data.
Okay. So the question then is this visual representation be helpful to interpret the latent space that you have in the acoustic model?
It's a great question that I had not time to look into. But in fact, because this model uses a shared encoder for computing audiovisual representation that are then used by one or the other decoder, we can assume that this space now encodes some visual features that could be also found through the same approach that we have used for acoustic features.
Okay.
And
because in your presentation you have the fact that some of the phonemes are very captured very quickly.
Mm-hmm.
So you have a large amount of layers that actually encode many things.
Mm-hmm.
So maybe too much. I don't know.
Mm-hmm.
Is it a too large pipeline, or is it something that can be explained using these visual embeddings? Why you have such kind of thing?
So actually, you have seen that in the results, the phonological feature were encoded very early into the model, but the acoustic feature, for example, were encoded later, and some of them at the very end of the model.
Mm-hmm.
So even though for some of the feature we could think that all these layers are not necessary, in fact, because some of the features are encoded at the very end of the model, it makes sense to use all these layers. But these methods could also be applied to a variation of the same model with different number of layers to see indeed if the encoding of this feature is delayed because the model has numerous layers, or if it could also work from for smaller models.
It depends where you learn the task and that kind of thing. But it's just we need more fine-grained analysis. That's what I mean. So maybe using more modality can be helpful in that way.
Yeah, true.
Thank you.
Thank you.
Okay, thank you very much. Thank you very much, Martin. So I will now ask our last speaker to come over. So the last speaker before the coffee break, please come here, is Nakanyseth Vuth. And I guess we are getting younger and younger presenters. So Nakanyseth is in his first year PhD student. Nakanyseth, the floor is yours.
Thank you. Hello, everyone. Just a brief introduction from my side. My name is So my name is Nakanyseth, but please call me Andrew because it's easier for everyone. Currently I'm a first year PhD student at the University of Grenoble Labs. I work in a research team called Generative of Lenglet under the supervision of Professor CNRS and Professor Didier Swap. So today I will be presenting to you about a new framework that I've been developing to generate annotated syntactic data for information extraction tasks. So I'd like to start this presentation with just the problem statement of the topic. Okay. I believe everyone who's working on NLP topic can agree with me that information extraction model rely on the availability and the quality of training data. And usually when it comes to training data, we oftentimes face two kinds of problems. First one is data scarcity. It can be very hard to find enough training data for your models, especially when it comes to specialized domain model. And beside this, you also have the problem of security risk. Because when you train your model, you also want to make sure that there's no confidential information that is included in the training data set. For example, this could be your patient's information. So one solution for these problems is to use a method called data augmentation. This is one of the common approach in this field. This is called rule-based word replacement. This idea is very simple. Let's say you have a sentence. So you create a heuristic to select random words in the sentence, and then you just replace the random words with other words. So these words could be retrieved from either using a dictionary, a thesaurus. You can also use word embedding model to calculate the semantic similarity and choose the word. You can also use a language model to predict the mass tokens. So some research even tried to approach this method on a sentence level, where they just use dependency tree. They parse the sentence, and then they transform the syntax of the sentence. For example, you have the sentence, John is doing his homework. It could be then transformed into the homework is being done by John. Although this method works, it comes with one big problem, and it's the problem low semantic and lexical diversity. And this is because the new generated data oftentimes convey very similar information to the original ones. Another approach is called back translation. This is also a very straightforward method. You have a sentence in one language, you translate to another language, and then you back translate to your original language, and then you have your rephrased version. But it also comes with this one problem as well when it comes to label. And this is because the label from the original data oftentimes will no longer be aligned with the new data. As you can see here, after you translate it, the hypertension becomes anti-hypertension, and the index of the word become misaligned. So these problems that I just introduced are the things that I'm trying to solve with my framework. In fact, this framework of mine consisted of many ingredients for which large language model, in-context learning, and distant supervision plays a very big part. So we formalized the task of creating annotated syntactic data as a natural language generation task. So the intuition is that, let's say you have a goal data, let's say you have a goal text T that is derived from your goal standard data, and you have a knowledge graph KT which describes the goal text T. So basically the knowledge graph KT is just a construction from the annotation from the text. The idea is that you use the knowledge graph KT as an input to build a prompt template P to prompt the LLM to generate a syntactic version of the text T, which is T prime. So here we define AT as a set of label annotations, and RT as a set of relation between the labels. And we say that AT and RT is a subset of knowledge graph KT. And so to get the annotation from our new generated text, we simply apply this method that is based on distance supervision, where we say, okay, for a given triple in the knowledge graph, if the head entity and the tail entity exist in the text, we said that these two entities in the text shares the same relation as the one in the knowledge graph. So we simply apply this idea to the knowledge graph KT and syntactic text T prime, and then we just filter out any node or any entity that's not appear in the text. So we get our knowledge graph KT prime, which we can then derive our annotation from. This diagram here shows you the full picture of how the framework works. So again, we start with our knowledge graph KT. We use this knowledge graph as input to retrieve k-shard example from a graph store. So the graph store here is the store that store all the embeddings from the graph. So basically what I did is that I embed all the knowledge graph from our goal data standard. And then I use the embedding to retrieve a k-shard example to build a prompt template P. So the idea here would be to prompt the LLM to generate us a text. But here, instead of prompting it one time, I prompt it multiple times. And then I create another prompt template to prompt the LLM again to select the best text D. And this is because text that is generated from LLM are prone to have hallucination. This is why we need a heuristic to make sure that the text that is output for us is a good text. And so because we recognize as well that the text that is generated by the LLM could introduce new entities, this is why we create another prompt template to prompt the LLM again to annotate the entity first. Here we also apply the same idea. We prompt it multiple times and merge the result together. It is very similar to the idea of you have one text, and then you give it to many annotators to annotate the text, and then you merge the result together. So the result that is merged will be then merged again with the knowledge graph KT prime that I just presented you in the previous slide. So based on this framework, I managed to do two kinds of experiments. First one is on an English general domain, where I tested on the task of name entity recognition and document level relation extraction task. Another data set I tested on French security defense, where I tested on event, attribute, name entity, and document relation extraction task as well. And the large language model that was used was a fine-tuned model based on Mistral AI 7B. So I managed to write two research papers based on the framework and experimentation. One is a collaboration with the people from Airbus and Avista. It just got accepted to a conference in Spain called CAS. Another one I submitted to an ACA workshop, which I'm supposed to receive the answer by this week, but I still haven't seen it. I think I do not have time to go into detail, but I can show you some experiment results. So this table here represents the performance of event extraction task. On the left side, you see the performance when you don't add the syntactic data. And the right-hand side is the performance when you add syntactic data. So we see a very good trade-off, a very big increase of performance on event classes with the low support. And we noticed the same trend for attribute extractions, but sadly not for entity recognition, which is the thing that we're trying to study. Okay, so to conclude this presentation, I'd like to give just some perspectives. So in this work, I managed to develop a generic framework to easily generate syntactic data. And I believe as well, this framework can be easily used for data anonymization. And this is because we're in control of the input knowledge graph. So that would mean we can just switch out any entities or any node that contain confidential information. And then we can just replace it with any random entities. So within the same idea, I believe as well, we can also perform bias mitigation. We just have to manipulate the graph in a way that it generates us an unbiased text toward a certain demographic. So thank you everyone for your time. Yeah.
Thank you. One quick question. So, okay, just a very quick question. So, what's the next step for you among the perspectives you have mentioned?
Actually, the next step is to improve the annotation quality, because even though it can generate us some annotation, the annotation is still far from perfect. So the goal is to somehow go back to the framework and somehow work on some part of the framework to improve first the generation quality and also the annotation quality.
Okay.
Yeah.
Okay, thank you.
Thank you.
Okay, so we have 20 minutes, I think, coffee break, and then we can resume for the second part of this session.